Okay, so good morning, and so let us begin today's lecture. We'll continue the study of the dynamics of a symmetric torque, and for a symmetric torque, hopefully you remember that I2 is equal to I1, and its need not be equal to I3. And if you put that in, there is some simplification in the kinetic energy which we had written out, and so you can see that it depends. T depends on uh, theta dot, phi dot, psi dot, of course. But you see only the appearance of the variable theta, but no dependence on you know phi or psi. Okay. So here, of course, phi, theta, and psi are the Euler angles, and I have not written out the center of mass kinetic energy either. That we can put in. Okay. So recall how we had done this. So we saw that the rotation matrix, which takes the laboratory frame to the body frame. We constructed it as a sequence of rotations. It was first about the z-axis by what? Phi. Then about the x-axis by psi, is it? And then theta. Right? It was a sequence of these three guys, and so let us just draw a picture to see how all these various angles work out. And so I have done that, and yeah, hopefully you can see the full listing. So we start out with EI, which is this is the lab frame, and do first. So phi, theta, and psi. So let me fix that. I have written theta and psi. Okay. So the first step we do is to go from EI, and we do a rotation about the z-axis by phi, and we get this frame which we'll call double prime. Okay, why double prime? Because single prime is taken over by the body frame, so this is our frame eventually. So I do that. So this is this phi rotation. So these blue axes. So first thing to notice is that since it's a rotation about the z-axis, E3 prime will be equal to E3 double prime will be equal to E3. It doesn't do anything to that, but these two will change. Okay, so that is this angle phi. This is what we get. Then what we do is we follow it up with a rotation about the x-axis. So now x-axis means that's the E1, new x-axis is E1 double prime, and that will not change under a rotation about that axis. So E1 double prime is equal to E1 triple prime, okay, which is this rotation about the x-axis by theta. Okay, so that's what happens. But now what it will do is you rotate E2 double prime to E2 triple prime by this theta, and E3, which is equal to E2 double prime, will go now to E3 triple prime. So that's the yellow axis that I'm showing. So you have E1 triple prime, E2 triple prime, and E3 triple prime. So that takes you to this thing. And the last one is a rotation now again about the new, it's about the z-axis with an angle psi. And did I mess up? Psi and theta, I think, yeah. What have I done? What was the angles that we did? Let me look it up. Sorry. Does anybody remember? psi, theta. Okay, so yeah, first phi, then theta, and then psi. So this is correct. So just need to correct one particular angle, which is, and this will be psi. Do I have people in my class? Because no one is able to look up something. I mean, I'm faster than you guys. Okay. It's not even funny. Okay, good.
Sir, psi is along Z, right? So Y is like E3.
Oh, so I got
Triple
it. So the
prime. So
theta
why
is
will it?
theta is correct, right? This picture is correct, is it? Yeah, it is. Yeah. Okay. Theta is the second thing, and then we are. So okay, thank you, thank you. I got confused. Okay, so this is good. And then finally, what we have is we make a rotation about the z-axis, which is now E3 triple prime axis. And now that we get these final axes are these guys. Okay, nothing happens to E3, so E3 prime is that. So these are our final axes. So let's just look at theta first. So theta is just the angle.
Yeah,
Yeah,
you
go
have
ahead.
mentioned again a rotation about Z. Is that fine?
Yeah, because it's about the new z-axis, because it's
Okay.
E3 triple prime, right?
Okay. Okay.
Yeah. Okay. So that's why E3 triple prime is the same as E3 prime. Okay, so we have this nice picture, and so the thing here is that the symmetry axis of the cone. So I've drawn a cone, but it's a cone is an example of a symmetric. The cone, I mean, the top need not be a cone. Okay, but I'm just using a caricature or an approximation to that. So E3 triple prime or E3 prime is the symmetry axis of the cone, and theta is the angle between the first z-axis and the final z-axis. Okay, this is kind of worth remembering that this is what is happening. Okay, and so now we want to put this in a gravitational potential, and so I will just do one thing out here, which is to okay. So let's say this is the location of the center of mass, and then mg will act downwards, and let's say that this length is h. Okay, so what I have in mind is that this cone is such that at a height, the center of mass is located at a height h from the tip. Okay, that's all. Okay, is this clear? So mg is like a force which is acting out there. Okay, so we need to now, so we'll put in what we will do is put in the the potential energy term for this, and also take care of the fact that so we'll do that. So we'll write the full action. Okay, is this picture clear now? What we have done? Okay, so
Yes.
okay, thank you. Let's now, yeah, good. Okay, so now that we have achieved that, and so we will also assume that the tip of the top is taken to be the origin in both the lab and body scale. Okay, so that is the point that is not moving. Okay, so this is so we'll just choose that. Okay, so now I mean clearly this implies that center of mass could be moving, right? Center of mass A should be taken into account. Okay. Okay, very good. Okay, so So there are many ways of doing this. So one thing is to just so exercise. Okay, the exercise is the following. I mean, it's kind of related to this parallel access theorem or whatever it is. So what's going to happen is that if you compute the moment of inertia about the tip, okay, then what happens is that then we already saw. So then what we will get is that we will get that, let's call these primes. So I1 prime will be equal to I2 prime, which will be equal to I1 plus NH square. Okay, so just coming back to this, so what you can see is that this point and this point lie on the z-axis in the prime E3 in the body frame. Okay, so the IZZ or whatever will not change, and it will also not mess up the diagonal part of this thing. So this is just H, because the shift is Y. The shift is just H times E3 prime. Okay, so so this is so all we have to do is so this will be the claim here. Okay, so the claim is what is the claim? So we saw that F m r dot square plus T should be the equal to total kinetic energy, right, including the motion of this thing. But I'm just going to claim is that so the claim is that this is equal to half I1 prime into whatever we wrote earlier, but with I1 replaced with I1 prime. Okay, that's all. Okay, you prove this. Okay, so this is the total kinetic energy. So we need to only write what is the potential energy. Mg times the z variable. So now we go back to this picture and see here. So that would be h into cos theta. Okay, mgh cos theta. Is this point clear? Okay. So again, so the remark is that so the Lagrangian L equal to t prime t minus v. Okay, where this where maybe I should just call this. I'll call this t prime so that I don't mess up. Okay, Lagrangian is t prime, and we see that it's a function of theta dot, psi dot, phi dot, and only theta. Even v is only a function of theta. So what can we say? The coordinates psi and phi are cyclic coordinates. Okay, I'll pause here. Are there any questions or comments about what we have done so far? All we have done right now is to compute the full kinetic energy and the potential energy and written out the Lagrangian. That's all we have done. Okay.
Sir, h is just the height of the from the tip to the center of mass and not the height of the top itself, right?
What? Repeat?
small h is the height of center of mass from the tip and
Yes.
not the height of the top itself.
Yeah, absolutely. So yes, correct. That is this.
And we can use the cone formula, right, for the location.
No,
of
it's not a
center of
cone.
mass.
It's not a cone. It's not a cone.
Okay,
It's not
okay.
relevant. It could be any shape. Any
Okay.
shape which has I1 equal to I2, not equal to I3. That's it.
Okay, sir.
Okay. Cone is one such example. But even something like this will be fine. Any shape, anything which you take surface of revolution will work. It need not even have, so, I'm just using a cone, but that is just a symbol. I'm not saying the actual. That's not relevant, I'm saying. Okay?
Okay, sir.
The shape is not relevant. So we get something very, very nice. We see that we get two constants of motion. Okay, first one is P5.
Sir,
Yeah, go ahead.
so what is the kinetic energy as differentiated from half mr dot square? What is the other kinetic energy?
Yeah. So I'm just saying that we have to put r dot square also, right? Because it's moving, right? And so I'm just claiming that this is equal plus t, which was just the rotational part, is nothing but t prime in this form.
Okay, sir.
Okay. So I have put that in because I've replaced I1 with I1 prime, which has this. It's a claim which you have to prove. Okay. This is not very hard, but you just have to sit down and define things properly, and then you will see. Okay. So P5 is just dl by d phi dot, and we can work this out. It's just I1 prime phi dot sine square theta plus I3 cosine theta into phi dot cosine psi plus psi dot. Some messy thing, it doesn't matter, but it's a constant of motion. And we'll see that P psi is dl by d psi dot. It's just I3 phi dot cosine theta plus psi dot. And if you remember our calculations, this is nothing but I3 omega. Okay? So this is what we have. We have two constants of motion. Are there more?
Sir, energy should also
Absolutely,
be constant.
absolutely. Yes. Energy. Because there is no time dependence. Okay. So we'll just hold it for a moment, and what we will do is that okay. So the point here is we can use first. Let us use the first thing. We can use the two constants of motion. P phi and P psi to eliminate phi dot and psi dot. Okay, so we need to write formulae for them. So let me write that. The page the phi dot. You can just invert things around. It's just P phi minus P and let's come back to this. Just one moment. Where did I define? Where did I compute P phi? P psi? Here. Okay. So we have to do some calculations out here, and so we get P phi as this thing. So we want to P phi minus P psi cos theta. If we do, that will cancel this term. So yeah. Okay, and once we do that, we can write psi dot as just one second. I'm trying to psi dot. I have some calculation which I don't like, so let me just do this fresh. Okay, so what we need is psi dot now, right? So we saw that p psi was I3 into psi dot cos theta plus psi dot. Okay, but we already know phi dot, so we can write psi dot equal to p psi I3 psi dot equal to p psi minus I3 cos theta into phi dot, which we already know. Okay, so once we divide out by this, so now what we see here is that we are able to eliminate phi dot and psi dot using the constant of motion. Okay, so let's now what is the formula for energy? Okay, so E will be equal to T plus V, right? So I just write that. Okay, but this is already we saw this is nothing but phi psi or right. This is a constant of motion. Okay, so I can actually define omega 3, sorry, E prime to be just, I'll drop this constant and that will just be equal to and so we are not done yet. What we have to do now is to go ahead and write trade this combination for P phi and P psi, and that's not very hard. Just check, it is half I1 theta dot square, but phi dot square sine square theta, if you come back here and see, it is it's just this. So you take this to this side. So if you look at phi dot, okay, so you just get plus P phi minus P psi cos theta whole square divided by 2 I1 sin square theta. Okay, plus m h. Okay, so what we see is that E prime of the Hamilton. So what we see is that there is a reduced. So this is a. So we see that now this is just depends only on theta and theta. Okay, and what we see is, even though this came from a kinetic energy term, this looks like a potential energy piece now, right? So this looks like a. So this whole thing. This is like an effective potential in the one-dimensional problem. Okay, is this clear? Is this point clear? Yeah. Okay, so we'll do one more change. We'll do a change of variable. Okay, so remember theta went from 0 to pi. So this implies that u belongs to the interval -1 to +1. Okay, and we can make this change of variable. And so what we will see is that, so let's do this, and I'll write everything in terms of u. So first thing we can do is what is theta dot. So theta, what is happening? There's some software update, and after which I don't understand what is going on. Okay, good. So let's be, the idea here is we just want to write it in terms of this thing. So what is theta dot? Is d theta by dt, which is equal to du by dt times d theta by du. Okay, so this is u dot, but what is du by du is cos theta, so du by d theta is minus sin theta. Okay, so this is equal to minus sin theta, but we have to rewrite sin theta in terms of u dot because we want everything to go that way, so it becomes u dot into minus square root of 1 minus u. Remember u is okay, so we have to just go ahead and keep substituting things, and so what we get, yeah,
du by d theta is minus sin theta, right? So d theta, okay.
yeah, thank you. No, I should have put the inverse. Okay, so this is what we get. So now we can just write e prime or h prime. I'll just leave it as e prime. Okay, so now we are in good shape. We have this thing, and so how do we go about? We still need to solve. So what are the inputs? Okay. E prime, p phi, p psi are determined by the initial conditions. Okay, and so okay, so remember how did we solve these things? So we would usually plot so in 1D problems we would plot, we'll pick a value of e prime, so we will have let's say we have something like this. To give me a particular value of e, we would draw this and then look for turning points, etc., and then look to solve the problem by getting all these turning points, etc., and we can do this thing. Okay, but we can also do the simple thing, which is the formal integration, which is to take this e prime is given here, so we can just write so formal integration in the sense that the integration may not be simple, but we can do it. Okay, we can the equation. u as a function of t, and hence cosine theta as a function. Okay, so we can do that. And so how do we do that? So let's go back here, look at this equation, and just take things to be e prime e phi minus e psi 2. So u dot will be plus or minus square root of okay. So this way we can integrate formulas. Once we have u dot, so u will be integral plus or minus. Okay. Turns out that there are integral expressions that are in terms of elliptic functions. Okay, but I will not. I will not do these things. So we will go back to our analysis of. So what we will do instead is let us analyze the turning point of the potential. Okay, so and what are these? So these are the zeros of the equation for u obtained by setting u dot equal to 0 in the expression for u. So what we will write is e prime is equal to whatever is that thing, u effective of u. Okay, so now the question is, what is the degree of the polynomial? So let me write out, for once let me write out u effective of u. Okay, so what is the degree? So this is e prime equal to u, but there's a 1 minus u square in the denominator. So to make it a polynomial, what we should do is multiply this whole thing by 1 minus u square. So what is the degree of the polynomial? Somebody?
2. 2.
3.
No, 3, because there's a u already here. You multiplied by 1 minus u. Okay. So degree equal to 3. Okay. And then this one thing we know about degree 3 polynomials is that it implies it has at least one real root. It can have 3. Is this clear? Because you can get for a cubic polynomial, there are only there are two possibilities, which is that all real, all 3 real, or 1 real and 1 complex conjugate pair, right? Because this is a polynomial, it's a degree 3 polynomial with real coefficients. There's nothing imaginary there. So over reals, if you take this thing, this is what we get. Okay. So let's just call this equation. Let's call the polynomial. Let g of u be equal to the polynomial, the cubic polynomial. Okay, we'll write it, which is just e prime into 1 minus u square minus 1 minus u square times u effective of u. Okay, and we are asking for the zeros. So first point is that we know that u is restricted between minus 1 and u1. Let's ignore this for a moment and ask how does it behave? How does it look for large u? Okay. The cubic term will obviously dominate, and so that just becomes g of u equals this m g h u cubed. Okay, so this is positive for large u, large positive u, and negative for large negative u. This below. Okay, so let me just draw some picture now. Okay, so let's draw this picture. And let's draw some axes first. Okay, so what we know is that it has some behavior like this, so it will increase. And let's say it has real roots. I'll draw the case of 3 real roots. So this is how it would behave. Okay, and so this is the function g of u. Let's use a different color actually. So this is what we get, and it has 3 zeros in this thing. And let's also put in the constraint that it is to be restricted, say, between minus 1 and plus 1. So let me draw some. So let's say this is Okay, so we are only interested. So now the whole point is also, so here there are 3 zeros, and I've drawn the case where all of them are uh, uh,
Real.
yeah, all of them are real, and also that this thing. Okay, so so this is just this thing. So there will be 3. I mean, in this setup there are 3 turning points, but let us look at. Okay, so yeah, so what this would what do we do now? Okay, so now the key point here is that the zeros of this polynomial are so let us look at, say, something like, so these. So what does this mean? What are the accessible regions for the particle? So this is like g of u. So it should be lie between the zeros, but let us look at what happens in this region. G of u, if you remember, g of u was E minus u effective, right? So if g of u is greater than 0, what does that mean? That just means that the energy is greater. So I just want to mark out the accessible regions. What are the accessible regions? Is my question clear?
Yes, sir.
Mm-hmm. So let's call this A, B, and C. So, and this is of course -1 and +1. So question to you is, G of u is less than 0. Okay. So G of u is less than 0. What does it mean? It means E is less than u effective value, right? Is that accessible region? No, right?
No.
So this is not an accessible region. Similarly, this is not an accessible region. Okay. So what we will see is that this and this is a boundary point, so that will also, so this is also an accessible. The way I've drawn this picture, assuming this is correct. Okay. So what we so the yeah so okay. So let's just focus on this region. Bad color.
So, sir, is this x-axis just u or u effective?
Which one?
I mean the horizontal axis,
It's little u. It's a u. It's a coordinate u.
not u effective.
That's capital U. Sorry. So sorry. Capital letter U is for potential. Uppercase.
So
And this is little u is the coordinate. I'm sorry. Maybe I should have called it V effective or whatever.
So,
Okay.
sir, the conclusions of the accessible regions
Mhm.
and the non-accessible,
Mhm.
we are drawing based on the thing that E is less than U effective or greater than U effective.
Yeah.
So, in the graph,
So it is like this. No, let's go back to this picture that I drew here, right? So to come here, so whenever the potential is greater than this is an inaccessible region, right? In this region, you're given a fixed E is given to you. So if potential exceeds, so E here, what is happening is E minus V is less than 0, right?
yeah.
That's all I'm doing. I'm not doing something very, very fancy.
So, in that
Okay.
graph we have,
Mm.
the current
Mhm.
graph,
Mhm.
The non-accessible regions are
Yeah,
marked where the curve is greater than the is above the horizontal axis.
yeah. That is because you look here in this definition here, you can see it's E minus U effective. So it's like a reversing of the potential. If you are drawing the potential, if I had taken G to be U effective minus E, then it would be like what we saw.
So shouldn't the horizontal axis should be U effective rather than just coordinate U? I mean, only then we can say that if the curve is above the horizontal axis, that means
No, no, no.
GU.
I mean, I define G of U this way. I define G of U like this, no? If I had
Okay.
defined it some other way, see, E, I mean, don't worry about these factors, but I just defined it as E minus something, right?
Yeah, okay, sir. Yeah, I got
That is what
confused.
I did.
Now it's clear.
It's not exactly E, it's not exactly E.
Yeah,
Actually,
okay.
yeah. Okay, but the thing
Thank
is,
you.
1 minus U square is always there. So I don't have to, I mean, this is equal to 1 minus U square minus E minus U effective. So all the signs I'm studying are correct. That's all I'm saying.
Okay, sir. Thank
Okay?
you.
Okay, good. So what we have, let's go back to white color. Why is this happening? Okay. So we will have, so at least in, so we will have bounded motion in, but anyway, in theta, in U and hence theta. Okay, so the picture will be, what was this? So theta can change. So theta obviously can change. So what will so theta dot will be changed. So what we will have is so let's draw something in terms of. So let me draw a slightly different picture in terms of maybe in theta language. So then it won't be confusing. So similar thing. So what we have is 0 and pi. This is theta. Okay, and then we have some V effective, which goes something like this. It blows up at those things. Okay, so if we choose a value of E, let's say we get these two things. So this is theta 1. Now I'm plotting V effective of theta. Okay, theta 1 and theta 2. Okay, and this will have some minimum. So E must be greater than this minimum value. Okay, so what we will do next lecture, we will carry out a detailed analysis of the full motion. Okay, so here we have roughly schematically seen how theta dot varies. Then you feed things back and then ask how does phi change, how does psi change, etc. We will see different kinds of motion, and this will so that will complete uh, the study of this symmetric top. So I'll pause here, or we just set up the problem and we have brought it down to an effective one-dimensional problem in theta. Okay, and that's it. Okay. So maybe I'll draw one. I will draw one picture for you to finish. This looks better. Okay, so what is going to happen is that just focusing on the theta motion, so what we're going to see is that so these are the turning points, theta 1 and theta 2, so the motion will look like this. Suppose we touch this. So this is what we will see. Okay, and this has a name. If it's varying between theta and 1 and theta 2, it's called nutation. Okay, so it will be periodic motion in theta, but that's about it. Okay, but doesn't mean the whole motion will be. If what I'm trying to say is we need not close. Okay, it depends on the other angles how they change. It's just an oscillatory behavior. Okay, so so we'll continue next time. Any questions, comments? Okay, so